Welcome to the third lecture on an introduction to large deviations. And today we are going to prove the Kramer theorem, which we formulated last time. And after that, we will discuss also rare events for vector-valued random variables, and then we will try to naturally come to the definition of large deviations that also I expect we will formulate today. And let me start with the formulation of Kramer theorem, which we want to prove today. I will write the name of section also, 2.3 is Kramer's theorem. And here we assume that we have a family of independent, identically distributed random variables, let C1, C2, and so on be independent, identically distributed, usually we write IID, random variables. And also we assume that random variables have the first moment with finite expectation, like C1, that we denote by mu, and it is a real number. And a cumulant generating function. We denote that function by phi, and let me recall that that function is defined as logarithm of the expectation of e to the power lambda xi, say 1. And also we denote, let also Sn, it is xi1 plus and so on plus xn. And and then we consider for every x that is larger or equal than mu, we have that the limit, and then n goes to infinity, 1 over n logarithm of the probability that 1 over n Sn is larger or equal than x is equal to minus phi star of x, where phi star is the Fenhill-Legendre transform, where phi star is the Fenhill-Legendre transform of the function phi, and this function is defined, let me recall, like supremum over all lambda x multiplied by lambda minus phi of lambda. And last time we discussed some properties of this function. We tried also to develop the intuition a little bit about the Fenhill-Legendre transform, also considered a few examples and so on. And today we want to prove the theorem. And let me recall that we already discussed the upper bound, because the upper bound was done as an introduction in the previous lecture, and we have shown that the upper bound is is namely that the upper limit n goes to plus infinity 1 over n logarithm the probability that Sn 1 over n Sn larger or equal than x is less or equal than minus pi star of x, and it was proven before. Um, uh, And today I would like to focus on the lower bound. The next proof. Lower. That is the limit from below n goes to infinity 1 over n logarithm the probability 1 over n Sn larger or equal than x less or equal than I'm sorry, so lower bound it is my larger or equal than minus phi star of x. And to prove the lower bound, here I would like to make some simplification. I want to consider the case when the cumulant generating function takes finite values. Here, for simplicity, we assume that phi lambda takes the real valued is a real valued function for every lambda from R. And by the way, many examples that we also consider here, it is exactly that case. And here I don't want to be very general. If you are interested how we can modify the proof or change the proof in the general case, I just recommend to go to the literature, for instance, which you can find in a lecture notes or just any literature about large deviations. And I'm sure that there you will be able to find the general case also when the cumulant generating function is infinite. Okay, to obtain the lower bound, I want to use the lemma that we proved last time, namely that the cumulant generating function, if it takes finite values, is continuously differentiable. We also know its derivative, and we know what is the derivative at the infinity. Let me recall that according to lemma in the lecture notes, it is 114, which was discussed last time, the function. Let me write that shortly, is from C1 R, and also the derivative at 0, it is the expectation. I recall that mu is the expectation of C1, and also phi prime of x goes to the essential supremum of the random variable, say xi1, as x goes to plus infinity. And this essential supremum we denoted last time by beta. Also, we will use the same notation. And now let's consider a few cases. So first of all assume that let's take a point y that is from the interval mu and beta. If that interval is non-empty, and also then using the fact that the function phi is phi prime is continuously differentiable, its derivative is continuous. Let's take a constant lambda 0 such that phi prime of lambda, so again, lambda 0 from, and this lambda 0, it will be larger than 0, such that phi prime of lambda 0 is equal to y. It is possible to do because at the function phi prime at 0, it is mu. At plus infinity, it is equal to beta. Then this function is continuous, and we have the intermediate value theorem, which tells you that between the two values, you can always find an argument, you can always find a point such that the function will take exactly the value that you fixed. And we used that here. And then having this lambda 0 here, the idea is that we want to change the distribution of random variables that we consider. And this approach you will see also later when we will prove, for instance, the large deviation principle for Brownian motion. And also you can do a similar trick for many other cases for proving the lower bound. And let me show how it works in the most simple example. Here I want to consider C1 tilde, C2 tilde, and so on be independent, then identically distribution random variables, let me write that shortly, IID, with the following distribution. The probability that psi I tilde belongs to B, the distribution is given as follows. It is the expectation, and instead of the usual distribution of psi, we take the density, we take e to the power lambda 0 psi e, and then indicator that psi e belongs to B. Of course, the right-hand side takes the non-negative values because everything here is non-negative, but the problem could be that this expectation, when, for instance, you take B is equal to capital omega, and then indicator is equal to 1, that the value is not equal to 1 that you want to have for the probability. Therefore, we need to normalize the right-hand side, and we will normalize exactly by the expectation 1 over the expectation of e to the power lambda 0 psi. That now the right-hand side is a distribution of some random variable, which we denote by psi I. Also, you see that this part here, it looks like Fenhill-Legendre transform, only the difference is that in Fenhill-Legendre transform, you have here the logarithm. Therefore, just taken here that to that part, the logarithm and exponent, you will come to the following. You can rewrite that as e to the power minus cumulant generating function at lambda 0, and then the expectation e lambda 0 psi I indicator psi I belongs to B. To compute the indicator of this complete object. And it is done for every B that from the Borel sigma algebra. Okay, now you have new random variables, and let's see what is the cumulant generating function for this new random variable, because in particular we want to know what the expectation is. And you know that we can compute the expectation using the derivative of Fenhill-Legendre transform. Let's write here psi I tilde of lambda. According to the definition, it is the logarithm expectation of e to the power lambda psi I tilde. And now psi I tilde has a density. So therefore, the expectation of this exponent, it can be rewritten as logarithm. Then you have this normalizing constant, minus phi lambda 0. And then you have the expectation, the density, lambda 0 psi I, and then multiply by e to the lambda psi I. This is the expectation. And now we can compute it, because using that the fact that logarithm of product is the sum of logarithms, you will have e to the power minus phi lambda 0 plus logarithm, and then expectation, and then e to the power lambda 0, lambda 0 plus lambda ci. And the function which is here, it is the Fenhill-Legendre transform of, it is the cumulant generating function associated with random variable xc, but at the point lambda 0 plus lambda. And this just logarithm will kill exponent, it is minus phi of lambda 0. Thus, then you can continue that computation and write that it is lambda 0 plus lambda, or lambda plus lambda 0, minus phi of lambda 0. And now you can easily compute the derivative, because everything what you did here, you just consider the linear shift, and then you also subtract a constant that is phi of at the point lambda 0. Then we can compute, as I said, the derivative, psi I tilde, but and 0, and it will be the derivative of the function here, and at 0 it is lambda, at 0 it is lambda 0, let me see, it is lambda 0, and we chose, you remember that we chose this lambda 0 by such a way that it was y. It was exactly the choice of lambda 0. So then you see that the expectation of new random variables ci tilde is equal to 1. So this change of the change of density allows us to obtain the random variables with the expectation y, and now we want to use that. We want to remark now that random variables psi I tilde are independent, identically distributed. Therefore, you have the law of large numbers. That implies that by law of large numbers, it implies that the probability that the mean value of that random variables, I will put here tilde, it means that it is the sum of new random variables, tilde, minus y, minus expectation is less than epsilon, must go to 1 as n goes to infinity. But on the other side, we can compute this probability precisely, taking into account that random variables xi I was obtained from xi using that additional density. And let me do that computation. So p 1 over n s n tilde minus y is less than epsilon. And it is equal to, you remember that it has to be, but by the way, now you consider, and you see that here it is a sum of random variables c1 tilde, c2 tilde, and so on. Actually, now you work with a vector, with like, with a complete family of random variables xi tilde, which are independent. So therefore, the probability, the joint probability of that random variables, it is the multiplication of probabilities. That gives you this the normalizing constant But since you multiply probabilities, it will be n times. So you multiply n times, you will get a factor n. Then you have expectation, and then you have the multiplication of densities. Psi n. And then you have the indicator that 1 over n Sn minus y is less than epsilon. By the way, here I play a little bit with different densities, different distributions, and so on. I will later propose you some exercises where you can just solving them. You will confirm yourself that these computations that I do, they are indeed correct. For instance, that. Then let's continue. It is e to the power minus n phi lambda 0. And then you have the expectation of e to the power lambda 0 as n, and then the indicator that the absolute value as n minus y is less than epsilon. And now you see that Sn here, 1 over n Sn cannot be, it is between y plus epsilon and y minus epsilon. If you take a look just on this event means that you have the point y, you have y plus epsilon, you have y minus epsilon, and the random variable belongs to that interval. Therefore, here you can estimate this as n by n multiplied by this constant. Then it is larger or equal than e to the power minus n phi lambda 0. And you will get, you estimate and you move that exponent outside. It will give us y plus epsilon also multiplied by n. And then it remains the expectation of indicator function. That is the probability. Is less than epsilon. You see that just when we continue, we will get e to the power minus n, or we can forget about that minus, and first of all write lambda 0 of y plus epsilon, and then minus phi of lambda 0, and then you have the probability. And now our goal is that from one hand side, you know that this converge to 1, but you want to figure out first how fast converge this probability to 0. And now you obtained the inequality which we want to use. Thus, consequently, let me copy that inequality and then I will delete it. Or maybe let me say it here. I want to write this probability first of all. It is lim n goes to infinity, and then 1 over n logarithm of the probability that 1 over n Sn minus y is less than epsilon. And then the inequality, since you wrote that one, this you move to the left-hand side. You have this inequality, so therefore this probability here, it is larger or equal than that probability multiplied by that object here. It is larger or equal than lim n goes to infinity 1 over n logarithm, and you have e to the power minus n lambda 0 then multiplied by y plus epsilon minus phi of lambda 0. and then multiply by probability of 1 over n s n tilde minus epsilon is less than epsilon. Now, as before, using the property of logarithm about the product, you will obtain the limit n goes to infinity, 1 over n logarithm exponent minus phi lambda 0, and then plus. Oh, here you should be careful because we work with lower limits. But you see that this limit, it will converge. Therefore, you may put here plus and write another lower limit, because one of the limits exists. And probability of 1 over n s n minus y is less than epsilon. And now let's conclude, conclude what we obtained here. You see that this logarithm and exponent will kill each other. You will have n here and n here. Everything that you will obtain, you will have n and this term in the bracket. It is minus lambda 0 multiplied by y plus epsilon minus phi of lambda 0. And this term here, that probability here, as we remarked before, it goes to 1.
Excuse
Thus,
me, and this will be a plus phi lambda, right? Because we had.
Thank you for the comment. It should be like that. So therefore we have minus lambda 0, so in brackets, the difference. And then you see that the probability here converges to 1. Logarithm of 1, it is 0. Therefore that converges to 0, 1 over n also to 0. Then this term, you don't have any problems here. You have just convergence to 0, plus 0. But you want to estimate that from below, and then you can write that it is also smaller or equal than, so this is, the left-hand side is larger or equal than then you just take infimum over all lambda. Not necessarily only for fixed lambda, but you just take infimum over all lambda, and you have minus lambda 0 y plus epsilon minus phi of lambda. Oh, I'm sorry, now no lambda anymore, no lambda 0, lambda. And when we move minus outside the infimum, you will get supreme. You will get minus supreme. So it is lambda from R. And you have lambda y plus epsilon minus phi of lambda. And when you recall the definition of Fenhill-Legendre transform, here, it is exactly what we obtained in the right-hand side, but we obtain it at the point y plus epsilon. Then the term here, it is minus phi star of y plus epsilon. Okay, now you can obtain, now having the estimate that that the mean value is so minus epsilon, so is between minus y is between minus epsilon and epsilon is can be estimated from below like that. You can this to get the estimate the lower bound for that the expression which is in the Kramer theorem. Let's take x from mu beta, and let's put y that is equal to x plus epsilon. for small enough epsilon. And then I want to consider the limit n goes to infinity, 1 over n logarithm, the probability 1 over n Sn is larger or equal than x. On the picture, it is the following situation. You have here x, then you are interested what is the probability that 1 over n Sn belongs to that interval, but you want to get the estimation from below. Then our idea is that instead of that point, let's take the point that is that is x plus epsilon. It is y. And then let's estimate from below the left-hand side by the probability that the random variable that 1 over n Sn belongs to that interval. It is larger or equal than n to infinity, 1 over n logarithm, the probability, absolute value 1 over n Sn minus y is less than epsilon. And we said that we estimated that probability from below. It was minus Fenhill-Legendre transform, but at the point x plus 2 epsilon. And now, as an exercise for you, you can prove the following, you can observe the following, that first of all, phi star of x is finite for x smaller than essential supremum. And also you can show that we already discussed that, and it was one of the homework exercises, that it is convex function. And from that, you can conclude that phi star is continuous. Because convex function, it must be a continuous function. Then you can send epsilon to 0, because left-hand side, it doesn't have any epsilon, only the right-hand side, using the continuity and sending epsilon to 0, you get the limit, that the lower limit is estimated from below by minus phi star of x. Okay, we finish the proof of the first case when x is between mu, the expectation, and beta. Now, the case when x is larger than beta, I leave you as an homework exercise, because in that case, phi star x is equal to plus infinity. And then the lower bound false. Because the right-hand side, it is equal to minus infinity, and then so anything here is always satisfies that inequality. And it remains only the case when x is equal to beta. And in this case, we can make the precise computations, because for x is equal to beta, you have lim n goes to infinity, 1 over n logarithm, the probability that 1 over n Sn is larger or equal than beta. Actually, beta is like maximum or like supremum, and then the empirical mean is larger or equal than this maximal value. It can be only possible when all random variables are equal to that value. Therefore, you have the limit n goes to infinity, 1 over n logarithm logarithm, and here the probability that C1 is equal to beta, and so on, Cn is equal to beta. And now random variables are independent. Then the probability of intersection you can write as the product of probabilities. And all random variables have the same distribution. Therefore, you will have the power n here. And then using the properties of logarithm, you see that it is logarithm. It is logarithm of the probability that C1 is equal to b. And now it remains to compute the Fenchel-Legendre transform also for x is equal to beta, and see that we come to the same probability. Let's do that. Phi star of beta is equal to supremum. Lambda belongs to R. And then you have lambda, and now x is beta, and minus phi lambda. And now it is, and you remember that last time when we discussed the Fenchel-Legendre transform, and we obtained the upper bound in the Kramer theorem, then we make remark that that function is negative for negative lambda, and also it was as an exercise for you. Then we can write that supremum as supremum for non-negative lambda, lambda beta minus phi lambda. And then let's continue, because that's that supremum. You can write lambda beta, you can write as minus logarithm, and then the expectation e minus lambda beta. Of course, it should be clear why it is so, because that is constant. Expectation gives you nothing. Expectation of constant, it is constant. So therefore, it makes sense here. And then taking the logarithm, you will get minus lambda beta, and 1 minus again. It is exactly what you have here. And I wrote that in this form because also the cumulant generating function can be written in the same form. It is minus logarithm expectation e to the power minus lambda c, say 1. And then you can put everything together. You will see minus logarithm. And then there is expectation e, and then you will have the product. Maybe so this expectation is not needed. I'm sorry for that. Let's write that without expectation. Then you will have the product inside the logarithms, and then you can move exponent inside. Then you will see that it is minus lambda, and then beta minus c. I'm sorry, here is without minus, and then will be minus c1. And let's discuss, or let's consider what happens here when we compute so the supremum. Also, let me write that supremum like minus infimum. It will be probably more clear. The logarithm, the expectation, e minus lambda beta minus c1. And now you want to compute that infimum. But you see that if you change lambda, when lambda increases, then the infimum, then the function inside infimum, it will decreases. So because of the monotonicity. And therefore, you can reach that infimum when you send lambda to plus infinity. But now when you send lambda to plus infinity, then it happens here the following. For omegas that psi is strictly smaller than beta, you will have that this one will go to minus infinity, and therefore exponent for that omegas will go to 0. But for omegas where c is equal to exactly beta, this term will be equal to 0, and therefore you will have only that you will have 1. then, so because of this reason, you can see that you will obtain that minus, and then you have logarithm, the probability that psi1 is equal to beta. Okay, let me probably explain this more careful. I want to compute the limit expectation of E, or without, first of all, without that, minus lambda, and we have beta minus xi1. And then I will put here omega, just I want to compute the limit for every omega. Therefore, for if psi1 of omega is smaller than beta, then this will converge to 0. But if xi is xi of omega is equal to beta, then it converges, this e to the power 0, it is 1. Then the expectation using the dominated convergence theorem, you will have that lambda beta minus xi1, it goes to the expectation of the indicator function that xi is equal to beta. And that is the probability that xi is equal to beta. That phi star, it is minus logarithm of the probability. But what we have in the Kramer theorem? In the Kramer theorem, we have the estimate with minus phi star. You see that we want to obtain for x is equal to beta this inequality. So therefore, what we computed here, that is logarithm of 2, must be larger or equal than minus the result that we obtained. And it is exactly that we obtained it, because when you start with that, it is a probability, and it is, in this case, it is exactly equal minus logarithm. That gives you problem plus. Then we have finished the proof. Now, after this proof, we can go to the discussion of the definition of large deviation principle, which we want to introduce. Then the next section, I need to clean that part. Then the next section is definition of large deviations. Large deviation principle. And 3.1, large deviations for Gaussian vectors. Deviations for Gaussian. And here in this section, we want to consider the case how we can generalize our previous statement to the multidimensional situation, or even to the infinite dimensional situation. For instance, you have a sequence of processes and you consider the mean value. Of course, in that case, when you work with functions or when you work with vectors, you cannot write like the probability which we wrote here to obtain the statement. And then probably that like the natural object that you need to care about, it should be the probability that 1 over n Sn are not larger or equal than x, but belongs to some set A. And then we can also ask about how this probability will go to 0, how fast it goes to 0. Sn or to 1 or to anything goes, Sn goes to infinity. And To be sure that this question makes sense and this object is good enough to work, it would be nice to try to test this idea with some example. And as in the previous situation, like in the previous lecture, the nice example that you can easily work, it is the normal distribution. Because when you consider the sum of independent, identically distributed random variables with normal distribution, you again will get the normal distribution. And therefore, the question about the rate of convergence of this probability can be discussed with using the rate of convergence of the probabilities associated with the normal distributed random variables. And it is what we want to realize in this section. Then some notations. Now let's consider random vectors. Let's consider eta k1 and so on, eta k dim. It is standard Gaussian that are independent, identically distributed random variables or random vectors with the standard Gaussian distribution, independent, and also have distribution n0 and then the identity matrix E times D. So in other words, all random variables that you see here for k from n and also j from 1 to d, they are independent and normal distribution with expectation 0 and variance 1. And then you just take d independent copies, or dz vectors, you build the vector. You just take d independent normal distributed random variables, you form the vector, you get the vector eta k, and then you do that for every vector. And you have a family of independent identically distributed Gaussian vectors. And next, let me remark that the random variable 1 over n Sn has the same distribution as the random variable 1 over square root n eta belongs to A, where eta has also normal distribution with expectation I and covariance matrix that is identical. Because when you compute the covariance matrix of sum, you will see that it is exactly the covariance matrix of this random variable. And also, I want to continue here a little bit and write that this is the same as you just write. Eta belongs to the square root n multiplied by A. And now we want to estimate the probability which we obtained here. Our goal, rate of convergence of the probability that eta belongs to square root n A, when A is Borel measurable some set in RD. And let's start from the upper bound as before. Let me recall that the density of this random vector p eta of x, it is defined as the square root I'm sorry. So here I want to have that the vector square root n. I want to divide it. So therefore, the density, it is n to the power d, and then square root 2 pi to the power d, e to the power minus n, the norm x squared divided by 2. That's x, that is x1, and so on, xd from rd. And that is the usual Euclidean norm square. xd square. And now let's estimate the probability which we have them. The probability also, as before, we write upper limit because we want to get a kind of similar result as before, but we want to predict actually, or we want to see what we can obtain here. Goes to infinity, and then we can compute the probability, because probability, it is integral of the set A over the set A of the density. 1 over n logarithm integral A and then p eta divided by, I'm sorry, eta divided by square root n of x dx. That you know from your course of probability theory. And then we will work as before, that the logarithm and of product is the sum of logarithms, and then you have 1 over n. I'm sorry, I didn't say that. First of all, you need to use that, just write what the density is. And the density, it is square root n, I'm sorry for that, square root n to the power d, square root 2 pi to the power d. And you have integral of a e to the power minus norm of x square n divided by 2 dx. And then you use the property of logarithm. Apologize, we work with the upper limit. N goes to infinity, 1 over n logarithm. And here you have square root n, square root 2 pi to the power d, and here to the power d. But this function, it increases as a logarithmic function, and this decreases as that 1 over polynomial. And this product, that limit goes to 0. Therefore, the limit will exist, and then that the upper limit can be written as the sum of this limit that is equal to 0 plus, and then the limit n goes to infinity, 1 over n logarithm of the integral dx. And then we obtain it is equal the limit n goes to infinity, 1 over n logarithm integral a, and the exponent minus n, the norm x square divided by 2 dx. And after that, I would like to make some estimate from above, and in particular, this one I would like to estimate by supremum of the function over the set A. I put here supremum, y belongs to A, and then you will have here y. And in this case, you can easily, and then you get the estimate, and then you can easily compute the integral, and you will come to lim n goes to infinity, 1 over n logarithm. supremum is the constant. Now you can move it outside the integral, and also exponent is monotone increasing function. Therefore, you can move supremum inside the exponent, and you will have e to the power supremum. And then you move in minus outside the supremum. You will obtain minus, and then infimum and norm of y square divided by 2. I'm sorry, yeah, right? And then you have the size of the set A. And this and that here is denote the Lebesgue measure of A. It is Lebesgue measure. Of A. And now here for this computation, let's assume that the Lebesgue measure is finite. When Lebesgue measure is infinite, you need to be a little bit more careful doing this estimate, and this I leave for you just to do the computations, and you need to be more careful in the estimation of this integral in the case when A has infinite volume. But now I want to be as simple as possible. So therefore, we assume that the Lebesgue mass is finite. And then we can continue that the computation, and you see that logarithm of product is the sum of logarithms, and one logarithm, it will be logarithm of that exponent plus logarithm of this one. And after that, you need to divide everything by n. And then everything what will remain here, it is minus infimum, like, let me write first of all. Let's do everything step by step. 1n logarithm will kill exponent. You will have minus, and you can move outside, and divided by, okay, only n move outside, and then you have infimum of, here infimum y belongs to a, norm of y square divided by 2, and you see that it is exactly minus infimum of the norm of y square divided by 2, and then here is y belongs to a. Then we can summarize here and write that the upper limit n goes to infinity, 1 over n logarithm the probability eta divided, or we can even write Sn divided by n belongs to a. That was the limit n goes to infinity, 1 over n logarithm the probability eta divided by square root n belongs to a, and it was less or equal than minus infimum x belongs to the set A, the norm of x square divided by 2. Even you can write more, and I will do probably now at the moment not obvious step, but we will come back to that step later. Of course, you can here put the larger set, and when you take the larger set, infimum becomes even smaller, and minus infimum becomes larger. Then you can, for free, put here the closure of A. It is also true, either for A or for closure, where A bar is the closure of A. And now I want go back to the case to our first lecture where we computed the limit or rate of convergence for Sn defined as a sum of independent one-dimensional distributed normal distributed random variables. And there we obtained the result like in the Cramer theorem. And the right-hand side, you saw that it was x squared divided by 2. Let me recall that, just show you precisely. that it was our first example. And it was here. Here you can see the random variables that were independent, identically distributed with distribution with standard normal distribution. And you see that the limits which we had here were defined or were equal like minus and then x squared divided by 2. And the difference, only the difference that we obtained in our computations is that the upper limit is bounded not by that function itself, because here is no x, but it is bounded by minus infimum over the set of the function which you also saw before. Because in one-dimensional case, it is exactly the function which was in lecture number 1. Now I want to make the computation for the lower bound, for the lower limit, and see what I obtain there. The lower bound. And here we are interested in limit n goes to infinity, but now lower limit, because it can be that a limit itself does not exist. Logarithm, the probability, 1 over square root n eta belongs to a. And here, as before, we have lim n goes to infinity. And let me copy from the previous slide what we computed. And of course, I mean, with start, we have that term is the same. Therefore, it is the same. And therefore, this is the same. And also that part also is the same. But only the difference is that now with this limit, you need to change by the lower limit. Here by the lower limit, here lower limit, here lower limit, here limit is equal to 0, as we said, here lower limit. So therefore, what you can write only that term, but the upper limit you need to replace by the lower one. Therefore, I just copy that part and put it here. As we said, we just replace that by lower limit, just to avoid many computations. And now you want to get the bound from below. Therefore, you cannot just writing now infimum of exponent as we similarly as we did in previous case, but in previous case we wanted to get the upper bound and we wrote supremum, and then the naive approach would be to put infimum. But when you put infimum here, just doing the estimate from below, you put just infimum, you will move it inside the exponent, and here you will get infimum here minus, and then you put infimum, you will get supremum. And then doing a similar computations, your result will be like minus supremum. But it is not exactly what we want to obtain. At the end, we also would like to see that infimum here. So then we need to be more careful estimating the integral here. And now here the idea is, let's take a point x0 from the interior, from A interior. It is the interior of the set A, and let's assume that this set is not empty. Then in that case, you know that every point of the interior has a neighborhood that belongs to the set A. And let's take the radius small enough that the ball in the center of the point x0 with radius r belongs to A. The picture looks as follows. We have A, we have the interior. Maybe my picture is not very good here, but it is some interior of the point A0. And then you choose the point X0 and you choose the ball around that point with radius and radius here. It is R. And then you can estimate the integral as follows. The integral over the largest set is larger or equal than integral over the smaller set. And we can write that as a limit 1 over n logarithm. And here we integrate over smaller set over the ball. E minus n, the norm x square divided by 2 dx. And now let's remark that by the triangle inequality, the norm x, you can write as a norm. Well, first of all, that is not triangle. It is just, we just add and subtract x0. And then it is by triangle inequality, it is less or equal than norm x minus x0 plus norm of x0. But if you take x from the ball, then you can continue and write that the norm is less or that the radius plus the norm of x0. Oh, therefore, this x which is here, which is from the ball, you can estimate from above by this sum. But here you have minus. Therefore, that term, so this expression with minus can be estimated from below. Exponent is monotone, logarithm is monotone, then everything you can estimate from below. E minus n, and then you have r plus norm of x0 to the square divided by 2 dx. And then you see now also that is independent of x. You can move it outside. And inside you will get only that the volume of the ball. It is logarithm e to the power minus n r plus norm of x0 square divided by 2 and multiply by the volume of the ball, which is finite here. Here we don't need to care about that. And again, as before, logarithm of product is the sum of logarithms. And then you have 1 over n logarithm exponent plus 1 over n logarithm of the volume of the ball, but logarithm of volume, it is a constant, therefore the second term goes to 0, and you will have only 1 over n logarithm exponent. But logarithm and exponent will kill each other, n and n here also. And what you obtained here, it is minus r plus norm of x0 square divided by 2. And it is for r small enough. For r small enough. But r is any small number. Therefore, you can make r, sorry, it is typo, square. You can make r going to 0. And when you do that, you see that this will go to the norm of x0 square divided by 2. Then we obtain it. That this probability is smaller or is larger or equal the norm of x0 square minus divided by 2. And this is for every x0 that belongs to the interior of the set A. Okay, if that is so for every x0, then it is the left-hand side is also larger or equal than supremum over such points. Then This implies that it is larger or equal than supreme x belongs to A0 of that minus norm of x. Now I will forget about subscript 0. That's right, like this, right? And now you can move minus outside, and you see that it is minus infimum 0 norm of x squared divided by 2. Just for the comparison, let me copy the upper bound here also. And the upper bound was, oops, I'm sorry. It is the upper bound. Good. Therefore, in particular, you see when this infimum and that infimum coincide, then you have exactly the equality, that then the limit exists and it is equal to the term. If not coincide, then everything what you have, it is only the estimate, the upper and lower estimate. And now I think you can predict what should be in the definition of large deviation principle. Oh, actually, it should be the same like here, that we are interested in that types of limits, and everything what we expect to get, it is that type of inequalities, but probably for some different function x. And next section, definition of large deviation principle. Then definition. Maybe before we will write the definition, let's say that and not necessarily like also let me tell here that here also I need to change that one, because this random variable, it is exactly that Sn divided by n. Let me write that in this form. And before we were interested in the empirical mean for independent, identically distributed random variables. But who said that we can focus only on, or we must focus only on the random variables which are like Sn divided by n, defined exactly by an empirical mean. We can have any family of random variables, and then we can be interested how fast the associated probabilities goes to 0. So therefore here, now I don't want to focus anymore on random variables as n divided by n. We will consider some family of random variables, probably indexed by epsilon, be a family of random variables on a metric on a metric space E. And E is a function from that space to 0 plus infinity, including. Then we say that definition 3.1 that we say that the family psi epsilon satisfies the large deviation principle LDP, shortly we write LDP in the space E with rate function I if for every Borel set A, for every Borel measurable set A, we have that minus infimum of that x belongs to A interior the rate function is less or equal than lim epsilon goes to 0, but now we wrote 1 over n, now we write epsilon logarithm, the probability psi epsilon belongs to A. And of course that, so it is a lower limit. The lower limit is always smaller or equal than upper limit. Then let me also put here the inequality. Epsilon logarithm, the probability psi epsilon belongs to A. And it is less or equal than minus infimum x belongs to A closure. I of x. It is the definition that we will work. Let me also here make a remark that sometimes we can work with sequences of random variables numerated by n. What then is the definition of large deviations? Just remark. That in the case of random variables psi n, usually then the definition of large deviations, then the large deviation principle is formulated as follows. It is as before minus infimum x belongs to A interior rate function less or equal lim n goes to infinity lower limit. But now we wrote before an, but to be more general, let me put here some sequence an logarithm the probability that psi n belongs to A less or equal and upper limit an logarithm the probability psi n belongs to A and less or equal than minus infimum I of x belongs to A closure for some sequence an that goes to 0. And by the way, now we have one example, and we have already proved that example, namely that when you take random variables that eta k, they are normal distributed with mean 0 and covariance matrix identity, the standard normal distribution, and are IID, then the family Sn, then the family Sn divided by n satisfies the large deviation principle in the space Rd with the function I of x that is equal to norm x squared divided by 2. And here the an is equal to 1 over n, according to the previous definition. And also, let me note here that you see that we said that Sn divided by n has the same distribution as eta divided by square root n. And then where eta is also has a standard normal distribution. And then we did the all computations for this random variable. But if you now just replace 1 over n by epsilon, and then instead of eta divided by square root n and consider square root epsilon multiplied by eta, in new notations it is the same. And now just assume that this epsilon, it is any positive number, then you can come to the same conclusion, and you will see that this, instead of eta divided by square root n, and then this family satisfies the large deviation principle. In RD, also with the rate function I of x, that is norm x squared divided by 2. Once again, the proof is exactly the same as before, but everywhere in our computations, you need to replace 1 over n by epsilon. And then you obtain the inequalities which are here when epsilon goes to 0. And it is also almost the same example like here, but now instead of the sequence, you consider the family of random variables indexed by epsilon. Later, you will see many different examples. In particular, we will try to generalize the Kramer theorem, and we will show that the empirical means for independent identically distributed random variables in Rn satisfy the large deviation principle with the function, with the rate function that is the cumulant that is the Fenhill-Legendre transform of the cumulant generating function. And for that we will use the Kramer theorem, and then we will show that for every set A you have this type of inequalities with I replaced by phi star. But it will be next time. And for today, it is everything. Thank you for your attention. And now maybe you have some questions, discussions, some questions, or we can discuss anything what you want. So sometimes I try to not give the lecture without some interruptions because it is recorded, and then I don't want to cut off so much videos. But probably now we can discuss anything, or maybe I should summarize everything what you saw up to now. So you remember that we started with some simple probabilities, with some simple question. Okay, we have something like in law of large numbers, and then we asked okay, we consider Sn divided by n that is larger than some constant, which is larger than the limit in the law of large numbers, and let's see how fast the probabilities goes to 0. And we saw that they goes to 0 exponentially fast, and also we could catch the constants so in the exponent that is defined by this by the Fenhill-Legendre transform of the cumulant generating function. But of course, this result, it is not very satisfied for us, because we can work with random variables in metric spaces. We can work not with empirical means, but with some other family of random variables. For instance, some particle system, And then we can consider the situation when number of particles goes to infinity, and you know that there is some kind of convergence, and then you are asked about how fast probabilities goes to zero. So you want to be very general. And then to understand how general we can be, we consider it here in this lecture, after the proof, we consider it a simple example. We just take something that we can precisely compute. And this something, it is the sum of normal distributed random variables. Because here we know the density, here we know that the sum, it is also normal distributed. And then we did this type of non-complicated estimates. And then we came to the result that instead of the object which we saw before, you just need to take the infimum over the set that you care about, that you put here. Okay, for lower bound, you need to take interior. For upper bound, you need to take closure. But anyway, it is like very good candidate for the definition. And then at the end of this lecture, we just took our observation and then we just formulated the definition of large deviation principle. And later you will see that it is indeed very nice definition, and you can develop very beautiful theory based on that definition. For instance, later you will see that if you take random variables, which satisfies the large deviation principle, and consider continuous functions of that random variables, you also will see that it satisfies the large deviation principle. You will know precisely how it can be computed. You will consider many different examples, and you will see that for all of that examples, you can say what the rate function is. And then later at the end, we will talk about the applications to some particle system, to some model where you also see how the theory is important, for instance, for physics or for people who study, for instance, hydrodynamics, interacting particle systems, as I already mentioned it, and so on. But it will be later.